In this recording, we're going to be looking at some examples of how to determine whether a salt solution is acidic, basic, or neutral. So from Monday, we did some calculations to kind of prove some of this to you, but just to review, a salt is an ionic compound, okay, composed of a cation and an anion. Cations are almost always metals, but not always. Okay, we'll look at the main exceptions to that I want you to know. And anions are nonmetals. They have a negative charge. Cations have a positive charge. Okay, so the general rule of thumb is that you need to first, when determining whether a salt is an acid, base, or neutral, is you have to decide whether the compound is a salt or is ionic. Okay, so same difference basically for our purposes. So you have to recognize it as being a salt. And then you need to determine whether each ion, in other words, the cation and the anion, is acidic, basic, or neutral. And this all hinges on remembering that, first of all, the stronger an acid, the weaker its conjugate base, and vice versa. The stronger a base, the weaker its conjugate acid. Okay, and it turns out, and this might be a surprise, especially if you weren't in class on Monday, that if you have a strong acid, the conjugate base is not a weak base. It's actually so weak that it doesn't act as a base. So it's a non-functioning base, right? So HCl, strong acid, Cl minus, the conjugate base, it is so weak, it does absolutely nothing. In other words, it does not affect the pH. On the other hand, if you have a strong base, the conjugate acids are so weak that they don't act as acids. So for example, we can think of the conjugate acid of KOH, or K plus OH minus. Okay, so remember you lose an H plus. Sorry, you gain an H plus to get the conjugate acid. So the conjugate acid of K plus OH minus is K plus water. Okay, and we know water is a weak acid. Okay, and K plus does nothing. All right, so the conjugate acid of KOH is in a sense K plus. Right, so it's a little bit weird, but it's so weak it does nothing. Okay, so it's not even a weak acid, it's an ineffectual acid that does nothing. On the other hand, if you have a weak acid, its conjugate is a weak base. If you have a weak base, its conjugate is a weak acid. All right, so that's just a very quick review. We looked at one example, sodium fluoride. We broke it into its ions. And we decided, based on all of its characteristics, that since sodium has no effect on the pH, and F minus is a weak base, the salt, NaOH, the salt, NaF, is basic. All right, so let's look at another example. So for the second example, we have lithium nitrate. So the first thing, actually, the first step, it says, is to separate the compounds into its ions. Okay, but first of all, we need to determine, is this ionic? Is it a salt? So if we have something that's not a salt, like for example, HNO3 is not composed of a metal and nonmetal ion. Remember, this guy is just a strong acid. All right, so if you get a solution of HNO3 as your problem, you're not going to follow these steps because it is not an ionic compound. It is not a salt. It's not one of these, all right? But if we determine it's a salt, then we go through these steps. So lithium nitrate is a metal, lithium, and NO3, those are nonmetals, okay? So this is a common salt example. So the first thing we're going to do now that we have decided that it is a salt is we're going to separate it into its ions. So hopefully you're already going well. Lithium nitrate, Li, is the cation. The metal is the cation always. It has a positive charge. And then the nonmetal is the whole rest of it. All right, so that's something to remember, that you don't break the N and the O and the 3, like break that up. That's one poly, remember these polyatomic ions. Okay, and it's nonmetals. So there's your salt. Okay, so we said for alkali metals, we say, well, the conjugate base of Li plus is LiOH, which is weird. That's a strong base, so therefore Li is not acidic. Okay, or the other way to think about this is that Li plus is an alkali metal cation. Okay, and if you just remember that these are not reactive, that means that they do nothing. They don't affect the pH. Affect the pH. Okay, for NO3 minus, the first thing you do, okay, so alkali metals are easy. You just go, oh, alkali metal doesn't do anything, right? But everything else you have to look at. So NO3 minus, is this a potential acid or a potential base? Well, can it be an acid? Remember that acids give up H plus, right? Does NO3 minus have an H plus? No, there's no H in it, right? There's no H in the formula, so it cannot be a Bronsted acid, but it could be a base, right? So it's a potential base. So once we've identified that it's a potential base, then we need to look and see what its conjugate acid is. And remember, to get the conjugate acid, you add H plus, right? To get the acid, you add. And so adding an H plus to NO3, of course, gives us HNO3. So this is the conjugate acid of NO3 minus. All right, so is our conjugate weak or strong? So HNO3, is that a weak acid or a strong acid? Hopefully you're saying it's a strong acid because it's on our list. It's one of the 6 strong acids on the pink sheet, right? So since we know that the conjugate is strong, conjugate acid is strong, so HNO3 is a strong acid. Therefore, that's what this symbol means. Therefore, NO3 minus is so weak, it does nothing. Or nada in Spanish. Okay, so it does nothing. It doesn't act as an acid. It doesn't act as a base. It does neither thing. So will the ion generate H3O plus or OH minus in water? The answer this time is not one of these. It's no, it won't. It's too weak to do anything because its conjugate is so strong. So in conclusion, since lithium has no effect, okay, we learned that alkali metal ions are unreactive and NO3 minus is a neutral. Since it has no effect on the pH, it's a neutral ion. The salt, lithium nitrate, no effect, neutral, is neutral. Okay, so a neutral salt is one where both ions do nothing. In terms of reacting with water to make H3O plus or OH minus. So neither one of them do anything. So that's a neutral salt. Notice you have to go through these steps in order to decide whether a salt is acidic, basic, or neutral. So in our first example, we decided F minus was a potential base. We looked at its conjugate acid, okay, kind of like what we just did with the previous example. So, but then we realized, oh, HF is a weak acid, not a strong acid like HNO3. Okay, this is because it's not one of the 6 acids on the strong acid list. So since HF is a weak acid, we said then, oh, okay, if the acid is weak, the conjugate acid is weak, then the original ion is also weak. So that meant F- is a weak base. So F- does make OH- in solution. And that means that the salt ends up being basic overall. Okay, so since F- has a conjugate that's a weak acid, that tells us that F- acts as a weak base. So let's do another example. So we have NH4I, okay, so the first thing we have to decide whenever we do these problems is it a salt, first of all? This one's a little less obvious because it does not have a metal. Nitrogen and hydrogen and iodide are all nonmetals, so you need to recognize this as one of the exceptions. Whenever you see NH4 and another element, like I or a group of elements, you have to recognize this NH4 as being NH4 plus, all right? And this is one of the ions that you studied in Chem 151 and you should be familiar with, all right? Especially at this point, we've talked about it a lot as ammonium. All right, so I'll expect you to recognize this when you see it as part of a compound. I'll expect you to recognize that this is an ionic compound, okay? If I give you something more complicated, like say I gave you something like this, this is actually also a salt, but I would help you to recognize it by putting the charges on. So if I've written charges into the compound like this, I'm telling you it's a salt. So notice this N has an H and 3 carbon groups. We call these R groups. So it's got 4 groups total, all right? Which means it's not an amine, it's a protonated amine. All right? So it's not a weak base, it's the conjugate acid. All right? So, but in this case, NH4I, I would expect you to recognize that the NH4 is NH4 plus. All right, so this is the NH4 plus ion, and this is the I minus ion way down here at the bottom of the screen. All right, so the first thing you do is you break it into its ions, and then you decide, is this an acid or a base? Okay, in this case, it's a potential acid because it's not an amine, it's the protonated amine. It's got an extra H plus. It already has its H. Okay, so the NH3 has already reacted, gotten the H, and become NH4 plus. Right? And so the only choice this has now is to give up its H and go in the opposite direction, to go back. All right, so this is a potential acid. All right, NH4 plus. So what's its conjugate base? To get the conjugate base, you take off the proton. So NH3. Is the conjugate weak or strong? Well, this is one of our weak bases. It's one of those amines. A nitrogen with 3 groups, okay? 3 H's or 3 some H's and some R groups. All right, so since it's a weak base, since its conjugate is a weak base, so NH3 is a weak base, therefore NH4 plus is a weak acid. All right, so if you have one of these protonated amines, like up here, circling this up at the top, okay, if you have one of these protonated amines as your first part of your salt, as your cation, it's going to be an acidic salt because its conjugate base will always be an amine. Okay, so once again, if you have a protonated amine, like this one, or like this one, it's always going to be acidic because it's always the conjugate acid of an unprotonated or just what we call an amine. So will this generate H3O plus or OH minus? Well, NH4 plus is a weak acid. That's the one we're looking at. That's what's in this compound, right? It's not NH3, it's NH4 plus. So that's a weak acid, so therefore this ion in water, if you put this in water, let's go ahead and write the equation just for the fun of it. It can donate its H plus, give away its H plus to make H3O plus. All right, so it's going to make H3O plus. So for the I minus ion, okay, so far we know that NH4 plus is going to act as an acid. Okay, so this is an acid, but we still need to look at the other ion. We have to look at the I minus. So remember, we're looking at NH4I. So now we look at the other ion. So remember, you look at both ions. I minus, is it a potential acid? No, it has no H plus. The only thing it can do is be a base, so it's a potential base. Remember, we cannot decide if it's basic until we look at the conjugate. We cannot decide if the ion is acidic until we look at the conjugate, right? So this is a potential base rather than a potential acid because it doesn't have any H's. No H's, can't be an acid. All right, so what's its conjugate? If it's a potential base, we want to look at its conjugate acid. What's the conjugate acid of I minus? Well, we're going to add an H plus, right? To get the conjugate acid, you add H plus, so this is HI. Is this conjugate, this HI right here, weak or strong? HI is on our strong acid list. So therefore, it's a strong acid, right? So the conjugate is strong, so HI is strong, HI strong. Therefore, I minus is so weak, it does nothing. All right, so will the ion I minus, which is part of our salt, remember, will it generate H3O plus or OH minus in water? Well, it does nothing, so it's not going to do either. So the answer to the question is no, it won't generate either one. So since NH4 plus is acidic, according to our analysis above, I minus is neutral, it does nothing. You put them both in solution together, okay, this breaks apart, makes NH4 plus and I minus. This one acts as an acid. This one is a spectator ion, does nothing. So overall, the salt is acidic. Okay, so you break apart salts, you look at both of the ions, and decide from there what they do. Okay, so let's look at one more example. RbHCO3. All right, so this is ionic because we have the rubidium ion. Okay, the metal's the first part, the whole rest of it's your anion. We have HCO3 minus. Okay, so the conjugate base of Rb plus is RbOH. That's a strong base, so Rb is not acidic. So notice how the first ion, we're always testing to see if it's acidic, okay, usually, all right? The second ion, typically, we're going to test to see if it's basic. All right, and the other way we can tell that Rb is not acidic is that we know it's an alkali metal cation. These are not reactive. All right, so either way is fine. Okay, so for the second part, we have HCO3 minus. Now normally this would act as a base just by default, but in this case, this guy can do both roles. Remember, it's amphiprotic. Can act as both an acid and a base. We can tell this because it has a hydrogen, that it could donate and act as an acid. It also has a negative charge, so that's an indication it could act as a base, because negative stuff wants to accept positive stuff like H+. All right, so let's write the two equations. If it acted as an acid with water, it's going to give up its H+ and make H3O+. Or if it acts as a base, instead of giving up its H+, it's going to grab an H from the water. So the H is going to go over to make H2CO3. And water lost its proton, so that's OH-. Okay, so our question is, since there are two possibilities, what does it do? And in order to know this, we need to see which reaction is more favorable. The reaction of it as an acid or as a base. And there's a couple ways to do this, but the most common one is just to look up the K values for these two reactions. All right, so Ka for HCO3- is 4.7 times 10 to the minus 11th, and Kb for HCO3-, the Kb acting as a base, is 2.38 times 10 to the minus 8th. All right, so which one is more favorable? Remember, we want a larger K to get more product, right? And so the larger one is 10 to the minus 8th. Kb is bigger than Ka, and so therefore the reaction as a base is more favorable. And so that's the one that will happen to the greater degree. And so the reaction will generate OH- in water, okay, because it's going to act as a base. So since Rb+ is an alkali metal ion, and it does nothing, so it's neutral, and HCO3- is basic, this salt is basic. So notice when you have an amphiprotic ion, something that can both act as an acid and a base, like HCO3-, you need to know something else. You need to know the Ka and Kb for it acting as an acid versus acting as a base to decide what that particular ion will do.